Well, welcome to our next lesson on polynomial functions in one variable. In this lesson, we will be evaluating polynomial functions not only for real number functions or real number amounts, but also we will be substituting in variable quantities. And then at the end of the video here, we're going to learn how to analyze the graphs of polynomial functions so that we can determine what the end behavior is like, whether or not it's an odd or even degreed function, and also determining from a graph how many real zeros the function has. So to start off, I just want to explain again to go back and look at what function notation looks like. When we have the function notation that says something like p of 3, what that means is we are going to substitute in the value 3 for the variable x into the function p and evaluate it. So here we have a function p of x, and we want to know what this function p, what its value is at x equals 3. So all that means is substitute in the value 3 everywhere in the function where you see the variable x. And so we have negative 3 to the third power, so this means 3 to the third power and then put the negative outside. That gives us a negative 27 plus 9 minus 3. And then when we go ahead and evaluate that, we get negative 21. So the other thing that we're going to be doing is we will also be finding function values of variables by substituting variable quantities into the function. So here are some examples. Let's work through this first example. This one says, find q of a plus 1 minus 2q of a if you are given the function q of x equal to x squared plus 3x plus 4. So we're going to do this in parts. The first part we'll find is q of a plus 1. I called that step 1. Then in step 2, we will replace the variable x with the variable a, and we'll take 2 times that amount. Excuse me, and then we'll subtract it. So let's go ahead and start with replacing the variable x in our function with the variable a plus 1. So everywhere you see an x, we will replace that with a plus 1. Okay, so now when we square a binomial, remember we have to use FOIL to do that. So we get a squared plus 2a plus 1. And then distributing our 3, we get 3a plus 3. And then we have plus 4. So now we need to combine our like terms. We have an a squared plus 5a's and then plus 8. We add all of our constants together. So step 1 is complete. The next step, we're going to replace x with a and then multiply it by 2 when we're all finished. So instead of x, we want the variable a, and then we're going to multiply it by 2. So instead of x squared, we have a squared plus 3a plus 4, and then distributing our 2, we get 2a squared plus 6a plus 8. And then lastly, we're going to evaluate what they asked us to do in the beginning, was if we evaluate each of those pieces and subtract them, what do we get? So taking our answer from step 1 and subtracting our answer from step 2, we get a squared plus 5a plus 8, and then we're subtracting 2a squared minus 6a minus 8. I distributed the negative through the parentheses or through my answer here. And then combine your like terms. A squared minus 2a squared is a negative 1a squared. And then we have a plus 5a minus 6a is a minus a. And then plus 8 and minus 8 add to 0. So our final answer is negative a squared minus a. Oh, I forgot to put this step up there for you. That might have made it a little bit easier to follow through when I distributed my negative. All right, so this slide shows you the graphs of a variety of polynomial functions. And one thing I want to just remind you of is that the x-intercepts, wherever it crosses the x-axis, tells us the number of real zeros we're going to have. Notice with a constant function, it never crosses the x-axis. With a linear function, it crosses once. A quadratic might be twice, might not be at all. But you'll notice the correlation between the number of times that it crosses the x-axis and what the degree is of the function. End behavior is what happens to the function as x approaches either positive or negative infinity. So I've included this table that summarizes odd and even functions that have different leading coefficients. So for example, if I have an even degreed function, something like y equals x squared, its degree is even. It's a second degree polynomial. And if its leading coefficient is positive, then we know that the domain is all reals. The domain could be anything. And the range is all reals that are greater than the minimum value. So what this function tells us is the end behavior as x goes to positive infinity. As we let our x values get bigger and bigger and bigger, the function's getting bigger and bigger and bigger, going to plus infinity. As our x values go to negative infinity, our function value also goes to positive infinity. So you can see that represented right here. As x goes to negative, we should have an infinity symbol in here. Our function f of x goes to positive infinity. And as x goes to positive infinity, our function also goes to positive infinity. So here's an example with an even degreed function with a negative leading coefficient. And in this example, as x goes to negative infinity, as we go more and more negative, our function's getting more and more negative as well. So these both go to negative infinity. As x goes to positive infinity, our function f of x goes to negative infinity. And then an odd degreed polynomial, as x gets more and more positive, the function goes to positive infinity. And as x gets more and more negative, the function also goes to negative infinity. And then lastly, the leading coefficient being negative for an odd function. As our function goes to positive infinity, as x goes to positive infinity, the function goes to negative infinity. So we can add our infinity signs in here. And then as x goes more and more negative toward negative infinity, the function's going more positive to positive infinity. So let's look at some examples. It says describe the end behavior, determine whether it's odd or even degreed, and how many real zeros does it have. So in this first function, as we look at the end behavior, okay, as x goes to positive infinity, as we continue on the graph here, if we let x be bigger and bigger and bigger, at the end of the function, it's going more and more negative. So it's going to negative infinity. Hopefully, oh, I didn't write that in there. Okay, so I need to write this. So this one is going to negative infinity. And as we go more and more negative for our x values, the function again is going to negative infinity. So is our degree odd or is our degree even? Well, this one, since both of our end behaviors are going the same direction, we know that this is an even degreed function because it follows the pattern that our even degreed functions follow. And then the number of real zeros, we just have to look at how many times it crosses the x-axis, and we can see that it crosses twice, so there are 2 real zeros. Letter B here, our end behavior, as x goes to positive infinity, the function also goes to positive infinity. And as x goes to negative infinity, the end behavior also goes to positive infinity. The degree, odd or even, well again, both of my end behaviors are going to positive infinity. So again, this is an even degreed polynomial. And this one doesn't have any real zeros because it never touches the x-axis. Here are 2 examples for you to try. Go ahead and determine the end behavior, whether it's an odd or even degree polynomial, and how many real zeros it has. And bring those answers to class. See you next time.